So class, welcome to the lecture number 17th of the course PSOC. So in this lecture I will discuss about the speed governor system. Speed governing system. So we'll discuss about the speed governing system. So I will tell you the speed governing system. It is the most important topic in this course. So this speed governing system, okay. So this system is used to control the system frequency if there is any change in the load. Okay, for a sudden change or for any change in the load, the system frequency deviates, and this speed governing system, its job is to keep the system frequency constant under changing load conditions. So how the diagram of this system looks like. Let me draw the diagram first. So this system, we have two linkage mechanisms, two ridge linkage mechanisms. So this is one mechanism. Linkage mechanism means two rods, okay, like this, and we have another rod like this here. So I am saying this is point number A, this is point number B, and this is point number C. Here we have one more point here. I will say this is the point. I will say this is my point number D, and this is my point number E. Got it? So at point number B, I have a fly ball system installed here. So fly ball system is like this. Okay. So fly ball means I have two balls, two iron balls or metallic balls, and they are connected here with a spring. Okay. So this is the shaft of the turbine. Okay, this I am drawing as this is the axis of the shaft, and this is the shaft of the turbine. So this shaft rotates. So these fly balls, they will also rotate, or if this rotate, this point is also rotating, means here this is rotating like this, I will say, okay, in this direction or in this direction. Okay. So next, this is point A, B. At point A, I have speed changer. Speed changer means if I want to change the speed of this turbine, I have speed changer here. This is point A. This point is connected to this speed changer here. Okay. So what we do with the help of this speed changer, this is called speed changer. Speed changer. So with the help of speed changer, we can either shift this, move this, turn this point upwards, or we can turn it downwards. Okay. So like this is A, center is B, and this point is A, B, and C. Suppose I am raising this point A using a speed changer. So C is fixed. I will raise A like this. So obviously B point will also raise. Okay. If I am moving A upwards, okay, we are using the speed changer, B point will also move upwards. Are you getting it? How it will move? Because C is fixed. Okay. So now at point D, I have here a hydraulic amplifier. A hydraulic amplifier is connected here. Let me draw it a bit downwards. A hydraulic amplifier is connected here. Okay. So here okay, and I have a main piston here, and this E point is connected to this main piston. Okay. E point is connected to this main piston. Okay, so this is my hydraulic amplifier. So from this hydraulic amplifier, high pressure oil will enter. Okay, if this high pressure oil will enter here. Okay, if this high pressure oil, these are the two sliding contacts. Okay, this is called as pilot valve. This is called as pilot valve, and this is called main piston valve. Okay, and at this point E, this point is connected to the gate. Which gates? Steam gates. Okay, which will open or close the steam valves. Okay, so one point is here. So steam is coming from here, and this is the gate. If this arrow moves upwards, okay, what will happen to this gate? Will get closed, so lesser steam can will enter into the turbine here, and the shaft of the turbine is connected with the shaft of this fly ball. Okay, so if this arrow is moved downwards, means more steam can enter into the turbine, and the speed will thus increase. So these springs are called as restraining springs. Okay, so this is called as, from here I am saying steam is coming. Okay, and here steam is going to turbine. Got it? So this is the basic schematic diagram of a speed governing system. Okay, this is a basic schematic diagram of a speed governing system used on steam turbines for controlling the generator frequency at a constant level. Okay, so this is I'm saying this is a schematic diagram, okay, of a speed governor system which is used on steam turbines for controlling the generator frequency at a constant level. Okay, it is shown here. So what are the main components? The main components, this is the first component, fly ball mechanism. These are fly balls. These are fly balls. Okay, so first is this whole fly ball mechanism. The second component is this is whole called hydraulic amplifier. This is called complete hydraulic amplifier. Hydraulic amplifier. Third is the linkage mechanisms A, B, C and C, D, E. Okay. Fourth is the speed changer. Okay, this is speed changer. Got it? So what I am assuming, so before assuming, I will means I should once again explain the function of all the components. So I am saying there are mainly 4 components. Okay, first component is fly ball speed governor. This is called fly ball speed governor. These are fly balls. This is restraining spring, and this whole assembly is called fly ball speed governor. Number 2 is your hydraulic amplifier. Number 3 is your linkage mechanism. And number 4 is your speed changer. Okay, So I will explain, I will not write, but I will explain all these components one by one. So I have already made, I have already done my homework, so I will teach it here. Okay. So the first component is the flyball speed governor. Okay. So this flyball speed governor, it is also known as the heart of the speed governor system. So what happens, suppose due to any reason the speed suppose I'm saying due to any reason the speed increases. When will the speed increase? Maybe there is some reduction in load. Okay, so at that time the speed increases. So if the speed increases, what will happen? The turbine speed increases, means this turbine speed is increasing and this is also rotating at this same speed. Okay, because this is the turbine shaft and it is connected to the flyball system. So these flyballs are rotating. Okay, initially they are rotating at a constant speed. Okay, so I am saying if a speed increases suddenly, what will happen to these flyballs? So this spring will get expanded and these balls will move apart from each other. Okay, because of the expansion of the spring. So what will happen to this point, B point? So I am saying now these balls are right at these positions. Okay, so speed increases, speed of rotation of this fly ball increases. So the new position of the fly balls will be, suppose, this and this. Okay, so what will happen to, that means this spring is expanding. What will happen to point B? Point B will come down. Okay, so the point B shifts downward. Similarly, if there is some decrease in speed, what will happen to the spring? The spring, though it is rotating, but it is rotating at some speed. Suppose I am saying now the speed is decreasing. Speed decreases, what will happen to the spring? So these balls will move closer to each other. The moment these balls will move closer to each other, what happened to this assembly? So these will move upward, pushing the point B upwards. Okay. So this is what flyball does. It senses the change in speed and accordingly it moves the point B downwards or upwards. Okay, depending upon whether speed is increasing or decreasing. If speed is increasing, B will move upward. If speed is decreasing, B will move downwards. Okay. Now the second component is hydraulic amplifier. What this hydraulic amplifier does? Basically this hydraulic amplifier, if you will see, it comprises of pilot valve. This is pilot valve. Okay. And this is main piston valve arrangement. Got it? So it comprises of pilot valve and main piston valve. Okay. So you just see here this pilot valve. If you will see this what this hydraulic amplifier does, it converts the low power level pilot valve movement. This is a pilot valve movement. It is a low power level because point D moves upwards or downwards depending upon that. This pilot valve, it will move upward and downward. So it converts this low power level pilot valve movement into a high power level piston valve movement. And we need this high power level piston. We need a high power level piston valve because why? So suppose some steam is coming in this direction and we want to reduce the steam flow. What we have to do? We have to move the gate upwards, means we have to move the point E upwards, or we have to move the main piston valve upwards. Okay, so and we have to move it against the steam pressure. So it should be a high power. It should have some high power. Okay, so that is why we are saying it converts a low power level pilot valve movements into a high power level piston valve movement. Okay, because high power level is needed because we want to move this point against the steam pressure, high steam pressure. Okay, now the third is speed changer. Okay, what speed changer does? It provides a steady state power output, okay, setting to the turbine. How it provides a steady state power output setting to a turbine? Suppose I am saying that point A moves down. Okay, na? Point A moves down. Okay, what happens if point A moves downward? B is fixed, so point C will move upwards. B is fixed, A is moving down, so C is moving upwards like this. Okay, if C is moving upwards, what is happening? C is moving upwards, what will happen to D? D will also move upwards. Okay, So if D will move upward, okay, if D will move upward, what will happen? Look, if D will move upward, what will happen? This opening will open, because this block will move upwards. So this opening will open, and high pressure oil will enter from here, and it will enter into the main piston, pushing the main piston downwards. Okay, so high pressure oil will follow this path, and it will push the main piston valve downwards. And when this main piston valve is pushed downwards, the steam valve opens here. Okay, got it? So I am saying downward movement opens the upper pilot valve, so that more steam is admitted into the turbine under so that the more steam, because this point will further finally move down, so that more steam is admitted into the turbine under steady condition, hence more steady state power output. Okay, so the reverse happens for the upward movement of the speed changer. I'm saying now, if point A is moved upwards, this is fixed, point A is moved upwards, so point C will move downward. If point C is moved downward, point D will move downward. If point D will move downward, the moment point D starts moving downward, this opening will open. So high pressure valve is entered from this side, and it will push this piston now upwards, and it will close the steam valve, thereby decreasing the speed. Got it? So this is speed changer. And oh yes, I forgot this linkage mechanism used. So what is this linkage mechanism doing basically? So if you will see this linkage mechanism, it is used for transforming the flyball movement to the turbine valve. Flyball movement is transformed into the turbine valve through hydraulic amplifier. Okay, so what this linkage mechanism is used, I'm saying it is used for converting the flyball movement for transforming the flyball movement to the turbine valve through the hydraulic amplifier. So ABC is one ridge link, which is this point is, and this link ABC, it is posited at point B, and CDE is another ridge link which is pivoted at point D. So linkage mechanism, it will provide a movement. Okay, it will provide a movement to control the valve. It will provide a movement to control the valve in proportion to. So I am saying this linkage mechanism, it will provide a movement to control the valve in proportional to change in speed. Okay, in proportional to change in speed. And this link DE, okay, it provides feedback from the steam valve movement. How I am saying it will provide a steam feedback. Suppose I am saying initially point C moves upwards, so D will move upward, E will move downward. Okay, so I am saying C is moving upwards. This is like this. C is moving upward, so D will also move upward. D will move upward. High pressure oil will enter from this side, and it will push this main piston down. So the moment this main piston comes down, what will happen to E? So E is coming down also. Okay. So what will happen if I am saying this? If C is coming down, if C goes down, so oil comes from here and it goes here. So this E point is going upwards there at that time. Okay. Got it? So I am saying DE, it acts as a feedback from the steam valve movement. Okay. So in reality, we say the movement of these linkage mechanisms A, B, C and C, D, E, they are very small. They are measured in millimeters. Okay. So movement is measured in millimeters. Okay, but it can be calibrated in terms of resultant power increments. Okay, we are saying upward movements. No, we are saying, suppose that we are taking movements upwards or downwards. We are saying that upward movements are taken positive. Okay, and downward movements, upward movements are taken negative, and downward movements, they are taken as positive. So I am saying this is my A. So this is the movement of point A, XA. So this is the movement of point B, XB. Movement of point C is denoted by XC. Movement of point D is denoted by XT, and movement of point E is denoted by XC. Okay, so I am saying length of this link AB, it is LAB. Length of BC is LBC. Length of CD is LCD, and length of DE is LDE. Okay, you got it? So next, let me explain here. So I assumed that all upward movements are taken or assumed negative. All upward movements, they are assumed negative, and all downward movements, they are assumed positive. Upward movement negative, downward movements positive. You can also take upward positive and downwards negative. Okay, that is not a problem. So next, let us model the speed governing system. Okay, next is the modeling of speed governing system. Modeling of speed governing system. So initially we are saying that the system is operating under steady state condition. Steady state condition means this linkage arm ABC and CDE, it is stationary. So stationary means pilot valve is closed. Okay, pilot valve is closed, and this steam valve is open by some definite amount or definite magnitude. Okay, steady state means speed is constant. So if speed is constant, these position of these links, it will not change. There will be no movement in point A, B, C, D, E. Okay, it is fixed. Got it? Stationary. And we are saying this pilot valve, it is closed here and closed here. And this steam valve, it is open but by some definite magnitude, so that the turbine rotates at constant speed. Okay, so we are saying that the turbine is, at that time the turbine is running at constant speed with turbine power output balancing the generator load. Okay, where power generation is equal to the load demand. Got it? So next, I can say these conditions can be characterized. Okay, that is steady state conditions. I'm saying steady state conditions can be characterized by, number one, I am saying speed is constant. So F naught means system frequency is constant. Okay, number two, PG naught, which is the generator output, and this is equal to turbine output, which is equal to load. Okay, and third is XC naught. So XC naught is the steam valve setting. Why steam valve setting? So I am saying it is the XC naught means the initial steady state position of point E. Okay, which is represented by XE naught. Okay, here I am saying XC naught. Okay, so now these are the steady state condition, and we will obtain a linearized model around these operating condition. You know that you can linearize a non-linear system only around the operating point. So I am saying these are my steady state condition. Okay, steady state condition or equilibrium condition, and I will say that I will obtain a linearized model, incremental model around these operating conditions. Okay, now suppose that I am saying that I am increasing the turbine power by delta PC. Okay, with the help of this speed changer, I am increasing the turbine power by amount delta PC. What I am saying, I am increasing the turbine power by delta PC with the speed changer. Okay, so turbine power is increased with the help of a speed changer. So how can you increase the turbine power? Turbine power increase means this point should move down. Okay, with the help of speed changer. So what I am doing, I am saying for this let point A be moved. Let point A be moved downwards. Be moved downwards by speed changer. Okay, by distance delta XA. Okay, if you will see, if this point is moved downwards, if A is moved downwards, it will go like this. B is fixed. I am saying B is fixed. Right now B is fixed. I am moving A downwards, so it will move like this. Okay, so if A is moving downwards, what is happening to C? C is moving upwards. C moves upwards, D moves upwards. The moment D moves upwards, what is happening? More oil is entering into the from the upper side of the pilot valve, and it is pushing this main piston valve down. So means the gate will open. If the gate will open, more steam will enter into the system and more power will be generated. Turbine power will increase. So that's why we are saying for increasing the turbine power by delta PC with the help of speed changer, what I have to do? I have to move point A downwards. Okay, so I am saying for producing delta PC power, increasing turbine power by delta PC, I will move point A downwards by delta XA. Okay, so this I am saying this delta PC, it is the power command. Okay, or this delta XA, it is the power command which causes the turbine power output to increase. Okay, I am saying delta XA, it is the power command which causes the turbine power output to increase and is written by delta XA is equal to K times delta PC. Okay, means कितना मुझे पावर इंक्रीज करना है, ओके, या चेंज करना है, उसके अकॉर्डिंगली मुझे XA चेंज करना पड़ेगा. So where I am saying where delta PC is the commanded increase in power. Let me take a fresh page. I am saying where delta XA is the commanded increase in power. So I am writing delta XA is equal to K times delta PC and labeling it equation 1. Okay. Now with the movement of point A, where I have kept that page. So I am saying this movement of point A, okay, it sets into motion a sequence of events that will take place in this system. Okay. So first I am saying, okay, movement of point A, downward movement of point A will cause an upward movement of point C. Okay. So as point C moves up, point D also moves up. How? Suppose I am saying A, this is B, this is C. C, this is D, this is E. So look, this is, for example, my pen. Okay, so now I am saying first B is fixed. Okay, it is moving at a constant speed. System is moving at a constant speed. So all points are fixed. So now I am saying that I want to increase the turbine power by delta PC. For that, what I have to do, I have to move the point A downwards. So I will move point A downwards. It will, the new position will be like this. Okay, so with the downward movement of point A, point C is moving upwards. Are you getting it? point C moves upwards. So now come to this point. No, look, if I am moving point C upwards, so what will happen to point D? Point C is moving in here. Point D will also move upwards. Okay, so with the moment of when point D moves upwards, look here, when point D moves upwards, okay, so what will happen to the pilot valve? Pilot valve will also move upwards. So high pressure oil will enter from here, okay, on the top of the piston valve, main piston valve, and it moving it, and it will pull this main piston valve downwards. If it will move downwards, more steam will enter. Okay, so the turbine generator speed will increase and the frequency will go up. So I am saying the frequency will go up by an amount, say delta F. Okay, I am saying frequency will go up by, frequency increases by delta F. Okay, now with the increased speed, what will happen? Now as the speed increases, okay, frequency is increased by delta F. So means speed of rotation of this turbine shaft, it increases. So what happen if the speed of rotation of turbine speed increases, the speed at which these balls were rotating, it will also increase. So if the speed of rotation of balls will increase, so spring will expand and this point B will move downwards. And I am assuming that point B will move downwards by an amount. B moves down by delta XB. And the moment this delta XB, it will be proportional to delta F. कितना speed increase हुआ उतना delta B, उतना point B नीचे आएगा. So due to the downward movement of point B, okay, I am saying due to the downward movement of point B. Now I'm saying point B up down होगा. So what will happen to point B? Point B is moving down. Point C will also move down. So what will happen to this point C? Point C will also move down. So I'm saying point C will move down by delta XC. So this delta XC is proportional to delta XB and delta XB is proportional to delta F. So I will see delta XC will be proportional to delta F. So if you will see the moment of point C, it is contributed by two factors. Okay, the first is when point A was moved downwards. When point A was moved downwards, point C was moved upwards. So because of that, frequency increases. So with the increase in frequency, what will happen? With the increase in frequency, point B will move downwards. Sorry, point B will move downwards. So with the downward movement of B, point C will also move downwards. Okay, so I am saying movement of point C is contributed by two factors. Okay, so that is, I am saying delta XC, it is the movement of point C, it is contributed by two factors. Number one is delta XC dash, which is due to the movement of downward movement of point A, and delta XC double dash, which is due to the what I am saying, which is due to this downward movement of point B. Okay, so I am saying I am saying delta XC dash is the change in position of point C due to change in position of point A. Okay, and this delta XC dash can be obtained, it can be obtained by having point B fixed. I am saying initially when जब मुझे delta PC increase करना था, मैंने क्या किया था, A को नीचे लाया था, B को fix रखा था. ठीक है, A नीचे आया था तो C ऊपर गया था. So this upward movement of C here I am denoting it by delta XC dash. So I can determine the this delta XC dash, that is change in position of point C, which is due to the change in position of point A. How can I find it? Okay, I will show it here. How can I find it? I have drawn it here, but still I will try again. So I am saying this was my linkage mechanism. This was A, this was B, and this was C. So initially A was fixed, and to increase the power output by delta PC, I was moving this point by downwards. Suppose I am moving it downward by delta XA. So with the downward movement of this C will move up and this will be delta xc, but which xc dash? So I will join this like this. So this was length AB and this was length BC. Okay, so downward movement positive, upward movement negative. So can I write minus delta xc dash upon delta xa minus delta xc dash divided by delta xa is equal to LBC divided by L AB. Okay, you know the method of similar triangles, how, so it is a similar approach. So delta xc dash will be equal to minus delta xa LBC upon L AB. So I am writing it equation number 2. Okay, but we have also I also showed you that I also showed in the previous case. I am saying that delta moment of delta xa is directly proportional to the power increase in turbine output power. Okay, so using the constant of proportionality, K as the constant of proportionality, so I can substitute this delta x, and where delta PC is the commanded increase in power output of the turbine. So I am saying for increasing the power output by delta PC, I have to move point delta xa downwards. Okay, so using the proportionality sign, removing the proportionality sign, I can replace put an equal to sign here and write a constant of proportionality here. So I will substitute xa from here to here. What will I get? I will get delta xc dash is equal to minus LBC upon LAB. Okay, so what I am left with, K into delta PC. So you know that these lengths are constant, so these lengths will not change. So I can represent K into LBC by LAB by some constant which I can say is equal to K1. So delta XC dash is equal to minus K1 delta PC, and where what is K1? K1 is nothing but LBC divided by LAB into K. Okay, so I got delta XC double dash. So delta XC dash double dash is the change in position of point C due to the change in position of point A, and this point A position, we are changing the position of point A to increase the turbine output by delta PC. Okay, now second case I am saying, so because of this increase in delta PC, speed increases. So when speed increases, balls will move apart. Okay, because the spring will expand and point B will come downwards. Okay, now I am saying that point A is fixed. Here point B was fixed, point A is fixed. So A, B, see, this was LAB, this was LBC. So I am saying point A is fixed now. So what happens now? Point B will move down. Because of downward movement of point B, point C will also move down, and this will move down by amount delta XC double dash. This is delta XB. So again, using the concept of similar triangles, you will get here delta XC double dash divided by delta XB is equal to LAB plus LBC divided by LAB. Okay, now these lengths are constant, so I can write delta XC double dash divided by delta XB is equal to KB. Okay, because lengths are constants, so ratio will again the ratio will be constant. So I can write delta XC double dash will be equal to KB into delta XB. Okay, now remember, point B moves down, okay, by a distance. We know that how much this point B is moving down. Okay, how point B is moving down? I am saying the speed is increasing. Because of the increase in speed, fly balls are moving apart and point B is coming down. So movement of this, downward movement of this point B, okay, how much it will move down, it will depend upon what? It will depend upon how much speed is increased or how much frequency is increased. So can I write, I can write movement of point B, that is delta XB, is proportional to is proportional to change in frequency or increase. Change means increase. Here the frequency is increasing. Change in frequency delta f. So can I write delta xb is proportional, so I will use a proportionality constant here into delta f. Delta xb is equal to k2 dash delta f, where k2 dash is the cost of proportionality. So now can I replace delta xc double dash? Delta xc double dash was kb into delta xb. It is equal to kb into delta xb is k2 dash into delta f. So delta xc double dash is nothing but k2 delta f, where k2 is nothing, it is a product of two constants, kb into k2 dash. So we got the value of delta xc dash and delta xc double dash. So we can easily calculate delta xc. So delta xc was nothing but delta xc dash, which was minus k1 delta pc, and delta xc double dash, which is k2 delta f. You got it? यहाँ तक कोई प्रॉब्लम तो नहीं है? So these constants k1, k2, these constant, it depends upon the lengths of the linkage arms AB and BC, and also depends upon the proportionality constants of the speed changer. Proportionality constant of the speed changer was what? Proportionality constant of the speed changer was k. Okay, proportionality constant of the speed changer was, I assumed it was k. Okay, and proportionally constant of the speed governor also, because this is a flywheel mechanism, speed governor also, which I represented by kb. Okay, so this k1 and k2 will depends upon these factors. So okay, so you have we have means solved for the moment of point C. Okay, now let's see what will happen next. So I am saying next, because of the movement of point C, the point D also means moves from its reference value by some amount of space. I am saying delta xd. Okay, I am saying for small movement of point D from its reference position, that is delta xd, is the amount by which the, so अब D कितना ऊपर मूव करेगा? So D will move up. If D will move up, जितना D ऊपर मूव करेगा उतना ये ओपन होगा. Okay, so how I am saying it, I am saying for small movement of point D from the reference position, that is delta xd, okay, is the amount by which the pilot valve opens. Okay, pilot valve कहाँ से ओपन होगा? या तो यहाँ से होगा या तो यहाँ से होगा. तो जितना xd ऊपर, जितना D का मूवमेंट कितना होगा, उतना ही जितना pilot valve ओपन होगा. And this movement of pilot valve, it is contributed by the movement of point C, which is delta xc, and the movement of point E, which is delta xe. Okay, that means I am saying, what I am saying here, I am saying xd, movement of point C, it is D, it is contributed by D कितना ऊपर नीचे जाएगा, मीन्स पायलट वाल्व कितना ओपन या क्लोज होगा, ये किस पे डिपेंड करेगा? नंबर वन, ये कितना चेंज हुआ, ठीक है, तो इसको रिप्रेजेंट करूंगा मैं डेल्टा एक्स डी डैश, मीन्स कितना C कितना ऊपर नीचे जाएगा, उस पर डिपेंड करेगा कि पायलट वाल्व कितना ओपन या क्लोज होगा. दूसरा, D कितना मूव करेगा, वो किस पे डिपेंड करेगा कि E पॉइंट कितना चेंज हुआ, तो उसको करते हैं प्लस डेल्टा एक्स डी डबल डैश. Okay, now next I am saying let delta xd dash be the change due to delta xc, and can be, this delta xd dash can be obtained by having पॉइंट E फिक्स्ड. ओके, पॉइंट E को फिक्स करेंगे तो ये कैसे निकलेगा मेरा? दिस इज C, दिस इज D, this is E. No, I am keeping point E fixed. Suppose I am saying that when A point was moving downwards, so C point was moving upwards. So because of this movement of point C, so D will also move upwards. So this is delta x C and this is delta x D dash. Okay, got it? So delta x D dash divided by delta x C. Okay, so these are upwards moving movement. I told you what upwards movements are taken, positive or negative. Upward movements negative. So this movement negative, this movement negative, they both are negative. So negative negative will cancel each other. Okay, so xd dash means this is LCD, this is LDE. LDE divided by LDE plus LCD. So from here I can get delta xd dash is equal to, so these are constants, so it can be replaced by one constant K3 into delta xc. Okay, now suppose I am saying because of the movement of this xd as d moves upwards, यहाँ पे d पॉइंट ऊपर गया ना, जब d पॉइंट ऊपर गया तो यहाँ से ऑयल एंटर किया, ओके, और इसको नीचे किया, तो जो ही ये नीचे होगा तो e पॉइंट को क्या होगा, e पॉइंट भी नीचे जाएगा. ओके, नो नेक्स्ट आई विल सी द change in position of point D when E is with the change in position of point E. Now change what I am calculating, I am calculating the change in position of point D due to the change in position of point E. So how can I calculate it? It is easy. Now I will keep C point fixed, C D E. Now C point is kept fixed and I am suppose saying that this moves down by delta x E. So if this is moving down by delta x E, so D point will move down by delta x D double dash. Okay, so now I can calculate delta x D double dash divided by delta x E. It will be equal to LCD divided by LCD plus LDE. So delta x D double dash is equal to, I will replace it by some constant, this by some constant K4 into delta x E. So what is the net movement of point D? Delta x D is equal to x D dash is nothing but K3 delta x C, and x D double dash is nothing but K4 delta x E. So I am labeling it as equation number 4. So and where I have calculated xc, it is equation, I am labeling as equation number 3. Got it? So one more point is here which I want to explain. So I am saying that moment of point D, okay, delta xt, okay, this movement of this delta xt, it results in the opening of the pilot valve. Okay, movement of delta xd, it results in the movement of the opening of the this delta xt, it results in the opening of the pilot valve, which leads to the entry of the high pressure oil into the hydraulic amplifier. Okay, okay, then the downward then the downward movement, it will enter from here. Okay, as D moves upwards, I will say the oil will enter from here, and this main piston movement, it will move downwards. Okay, so and this as this will move down, so the gate will open, more steam will be allowed to enter into the turbine. Okay, so उसके बाद while means in this hydraulic amplifier, okay, I am saying two assumptions are made to represent the mathematical model of the movement of point E. What I am saying, I am saying two assumptions are made, okay, to mathematically model the movement of point E. The first assumption is, we are saying that we have in this hydraulic amplifier, we have pilot valve and main piston valve. Okay, so they we are saying that that the inertial forces of both these valves, that is pilot valve and main piston valve, they are negligible as compared to the external forces which are exerted on it. Okay, which are exerted on the piston valve by the high pressure oil. Okay, because oil enters from here and pushes it downwards, or it can enter from here and it will push it upward. So what I am saying, that inertial forces of the valves are negligible compared to the external forces exerted on the piston due to the high pressure oil. Okay, so and the second assumption is that as a result of the first assumption, where I'm saying inertial forces are negligible, the rate of oil that is admitted into the cylinder, rate of oil, kitna oil enter karega into the cylinder, it will depend upon the port opening. ये port कितना open होगा. ओके, और ये पोर्ट कितना ओपन होगा वो डिपेंड करेगा अपॉन द मूवमेंट ऑफ पॉइंट डी, कि पॉइंट डी का डिस्प्लेसमेंट कितना हुआ है. ओके, सो डिपेंडिंग अपॉन द डिस्प्लेसमेंट ऑफ पॉइंट डी, it will decide the rate of it will decide the rate at which the oil will enter into the cylinder. Okay, so once you know what is the rate of the rate at which the oil enters the cylinder, thus you can say that the volume of oil admitted into the cylinder, it is proportional to the integral of the port opening, okay, delta xd. Okay, it is proportional to the time integral of the port opening delta xd. Okay, and the movement of this point E, that is delta xe, it is obtained by dividing the oil volume by the area of cross section of the piston. Okay, what I am saying here, I am saying rate of oil that is admitted into the cylinder, it depends upon the port opening xd. Okay, and the movement of point E, okay, the movement of the point E, it depends upon what? It is obtained by dividing the oil volume that is entered into the cylinder divided by the cross-sectional area of this piston. Okay, the more the oil, okay, because area is fixed, the more the oil that is admitted into the cylinder, the more will be the movement of delta xc. So I am saying delta xc will be nothing but volume of oil entering not admitted into the cylinder divided by area of piston. Okay, so volume of oil admitted, it will depend upon what? पोर्ट ओपनिंग कितना है और कितनी देर तक पोर्ट ओपन रहेगा. मीन्स आई एम सेइंग द वॉल्यूम ऑफ द ऑयल एडमिटेड इनटू द सिलेंडर, वॉल्यूम ऑफ द ऑयल दैट इज एडमिटेड इनटू द सिलेंडर, इट विल डिपेंड अपॉन कितना पोर्ट ओपन है. ओके, एंड दिस पोर्ट ओपनिंग इज डिटरमाइंड बाय डेल्टा एक्सटी. नॉट ओनली कितना ओपन है, कितने टाइम तक ओपन है. ओके, सो आई कैन से वॉल्यूम ऑफ द ऑयल एडमिटेड इज प्रोपोर्शनल टू गिवन बाय 0 माइनस डेल्टा एक्स टी dt. This is the volume of the oil admitted into the cylinder, because we say volume of the oil admitted into the cylinder, it is proportional to the time integral of the delta xt. So what is the area? Area is A. So what I am doing, I am representing, I will write it like this: 1 by A integral 0 to t minus delta xd dt. So I will represent 1 by A by some constant k5 integral 0 to t minus delta xt dt. Okay, so this equation numbering I will keep it as 5th. Now this k5, it depends upon the fluidic pressure and geometry of the orifice and cylinder and geometry of the cylinder of hydraulic amplifier. Okay, so this was my delta xe. So if you can see equation number 5, you can see this is positive and this is negative. Why? Look here, I will show. This is positive, this negative, means if this goes up, this goes down. Okay, or if this goes down, x will go up. Okay, means if E point moves up, D point will move down, or if E point will move down, D point will move up. That is why positive and negative. How can you can say that? Look here. I am saying if D point moves up, so oil will enter from here, and this piston valve will move down, so E point will move down. Okay, if D is moving up, E is moving down. On the other hand, I am saying if D is moving down, so as the moment this moves down, so this port will open. Okay, so oil will move from here and it will push the piston upwards, and E point will move upwards. Okay, so that is why the negative sign, we are using the negative sign here. Okay, so we have equation 3, 4 and 5. Now take the Laplace of equation, taking Laplace of equations 3, 4 and 5. What will we get? What is the equation number third? So this is equation number third, delta PC. So can I write delta XCS is equal to minus K1 delta PCS plus K2 delta FS. What is equation number 4? Here I have drawn it. So it will be delta XDS. Delta XDS will be equal to K3 delta XCS plus K4 delta XES. And what is the Laplace of equation number 5? Delta XES will be equal to minus K5 by S delta XDS. Okay, so you will get these equations. So label it equation 6, equation 7 and equation 8. Now substituting 6 in 7th and then substituting the whole in equation 8. So what will you get substituting this 6th in 7th? You will get delta XEX is equal to minus K5 by S. delta XDX किसके बराबर है? K3 delta XCS plus K4 delta XES. Okay, now what is delta XCX? You have it given, it is given in equation number 6. So you can write delta XES is equal to minus K5 by S. K3 delta XCS, it is nothing but minus K1 delta PCS plus K2 delta FS. So bracket close plus K4 delta XES. Got it? So now I will solve it. I will get, if I will take XES term from here to this side, what I will get? I will get delta XES. I will take outside. So this is 1. So this is minus K4 K5 by S. It will be plus K4 K5 by S. Okay, into XES, which I have taken outside, is equal to minus K5 by S. What is left inside? K1 K3, K1 K3, but with a negative sign, delta PCS minus K2 K5 by S, K2 minus K5 minus K2 into delta FS minus K2, but K2 is it to be multiplied by K3? Yes, it is to be multiplied by K3 because K3 is here and delta is X, so it will be K2 K3. Okay, so minus K2 K3 delta FS. So solving this further, what I will get? So I am solving this last step. No, I am taking this last step here. So if I will take this last step here, so what will I get? If I will take the last step, what will I get? So I will get delta XES into 1 plus K4 K5 by S is equal to, it will be K1 K3 K5 K1 K3 K5 by S into delta PCS. Okay, so this is also so I am using negative sign here, delta Fs. This will be negative. So this is not negative because K3 is to be multiplied this. So it will be plus K2 K3. So minus here is because of this minus K1. So plus, so minus K2 K3 K5 by S into delta Fs. So you got these equations. So now what I am doing, if you will solve these equations by removing this S in the denominator, what will you get? Delta XES into, so K5 and K5 is means common. So what I am left with, so dividing whole equation by K5. Okay, so you will get XES is equal to K5 plus K4. Okay, do one thing, divide the above equation by S by K5. Okay, if I will divide the whole equation by S by K5, what am I left with? Delta XES. So instead of 1, I will be left with S by K5. Not dividing, multiplying the whole equation by S by K5. Okay, so what is am I left with? It is, if I will multiply 1 by S by K5, it will be S by K5. So multiplying this equation by S by K5, so SS will cancel and K5 will cancel. I am left with K4. So if you will multiply this term by S by K5, so you are left with K1 K3 into delta PCS. Similarly here you are left with K2 K3 delta Fs. Okay, so delta XCS will be equal to K1 K3 delta PCS minus K2 K3 delta Fs whole divided by K4 plus S by K5. So I can express the above equation like delta XES is equal to delta PCS minus 1 by R delta Fs multiplied by KSG divided by 1 plus S TSG. So this S here, it means Laplace. S TSG, this capital S means Laplace, and TSG means time constant of the generator, and KSG means the gain of the generator. Okay, so where R, I am taking R is equal to K1 by K2, which is the speed regulation of the governor, which is called as the speed regulation of governor. KSG will be equal to K1 K3 by K4, which is called as the gain of governor, and TSG is nothing but 1 divided by K4 K5, which is called as the time constant of governor. Time constant of governor. So based on this equation, I will draw the block diagram of the speed governor system. So what is the output? Output is delta XES, and what is input? Input is delta PCS minus 1 by R delta Fs. Okay, so how can I draw? What is the gain of the governor? Gain of the governor is KSG divided by 1 plus S. What is the time constant? TSG. What is the output? Delta XES Okay, so what is the input? Delta PC minus 1 upon R delta Fs. So I am saying this is delta PCS. So this is positive and the another one is negative. So what is the other input? It is 1 by R into delta Fs. So I will take it like this, 1 by R into delta Fs. So is this equation complete now? I have represented this equation. This block, it is representing the governor block. This is the regulation multiplied by del Fs, and this is the change in the speed governor position. Delta PCS minus 1 by R delta Fs into KSG divided by 1 plus STG is equal to XCS. So this is the block diagram of a speed governor system. So next is the turbine model. After that turbine model we will see, then we have the generator model from where we will get del Fs. So first turbine model, after turbine we will get generator model, we will drive an equation for generator model. So from the generator model we will get output as del Fs. So that del Fs will come here. Okay, so this is all for lecture number 17. So thank you very much.